Chapter 9 focuses on oral liquid medications. So last week I covered a little bit about liquids on the supplemental handout. So this should be mostly a review for Chapter 9. It is important to know that there are a lot of different types of oral liquid medications available. We can have solutions, tinctures, which a tincture is basically a concentrated herbal extract. I know CBD is very popular now, so you have CBD tinctures. You may have heard of those before. Elixirs, so those are going to always have an alcohol base. Suspensions, I'll show you an example of an oral antibiotic suspension here in just a little bit. Suspensions usually need to be reconstituted. Usually they have particles. The active ingredient is usually suspended in the medication, meaning that it's not completely dissolving. So usually suspensions need to be shaken well before they are given. And then we have syrups, which are sugar-based liquids. So things like cough syrups. The sugar is, usually used to mask some pretty bad tasting medications. Oral medications in liquid form, they do absorb faster than solids, such as tablets and capsules. So they do enter the bloodstream a little bit more quickly. They don't have to take the time to dissolve. Most liquid medications are dosed in either household or metric units. In the pharmacy, we prefer the metric system. So if you ever get an order from a physician that is written in household units, we need to make sure that the SIG for our patient is listed in metric units. So we will have to be using the conversions that we took a look at last week. Different administration devices. So the most common that we're going to be dispensing is in the pharmacy will be the oral syringes. We've taken a look at those a little bit in the lab so far. Also medication cups, droppers, and dose spoons. Those are more common in the household. You might have had those, you might have those for your children, or maybe when you were a child, those were a little bit more common. But now we tend to stick with oral syringes, especially for children, because they are more accurate and they are oftentimes easier to administer to a small child. They even have pacifiers that you can give liquid medications now to babies. So a lot of different ways we can get medication to our patients. If you're ever using a medication cup, this goes for the same thing. Anytime we're using a graduated cylinder or a beaker to measure out a liquid, we always want to make sure we're measuring at eye level. And we always want to measure from the bottom of what we call the meniscus. So here are some examples in your book. I'm on page 167. Just some examples of some administration devices. So you see the oral syringe, the medication cup, the droppers here, and then the dose spoons. And then on page 168, you can see those medicated pacifiers that are sometimes used now. But this here, so anytime we pour a liquid into a beaker or a cup, it's just naturally going to have a curve. And so we call that curve the meniscus. So we always want to make sure we're measuring at eye level. And we want to measure from the bottom of this meniscus. So, looking over here, if you were just looking at the side of the curve, it's going to be a little bit higher than where you're actually measuring at. So we'll do some practice with that in the lab. Third quarters, you have probably already done some of that, but good note to keep in mind there. Okay, so just as I mentioned last week, whenever we're looking at liquids, their strength is always expressed as weight per volume. So we would never just express a liquid strength in just weight. So you wouldn't say, you know, take 200 milligrams of a liquid because that doesn't give us a volume to measure out. So if your SIG that's coming from the physician is only giving you the weight strength or for the dose, you need to be able to convert that into a dose volume. If you're still struggling with that concept, I would definitely go back and take a look at the supplemental math lecture just for review. And then we're going to review that again here in this lecture as well. So keep in mind the difference between a dose and a dosage. That is listed um, for your reference. I put it on that green sheet that we had last week, and it's also on page 168. I've highlighted it here for you. So a dose, remember, is always the amount that's given at one time, whereas the dosage is the total amount that's given throughout the duration of the prescription. So the dosage is usually referred to as the quantity that we are dispensing. So keep in mind, a dose is only given at one time. And so we're going to be calculating dose volumes both with ratio and proportion and dimensional analysis. Whichever way you prefer, I would suggest that you actively practice that in your assignment, but also, make sure that you know how to use both of these methods as well. When we're looking for a dose volume, remember that we always set the dose that's being ordered equal to the strength that we have in stock. So here you can see that they've ordered 500 milligrams, and in stock we have a 250 milligram per 5 ml suspension. So what that means is in every 5 mils of our solution or suspension, there are 250 milligrams of active ingredient. So if they want the patient to have 500 milligrams with each dose, we can set that equal to our 250 milligrams per each 5 mils of suspension, and then we can solve for X to give us that dose volume. So remember, solving for X, we're going to cross multiply here. So 500 times 5 is equal to 250x. Then we would have to divide off the 250. So that's what is shown here. And that would leave us with 10 milliliters for our dose volume. And you can see that that makes sense because we know that 250 is half of 500. So if each 5 mils is giving us 250 milligrams, well, we're going to need to do that twice. So 5 times 2 gives us 10 milliliters. Now, using dimensional analysis, so remember dimensional analysis is using multiplication to solve for the dose volume. I'm going to write this one out just so you can see it a little bit better than what I have there on those slides. I think it helps to see it when your fractions are vertical here. So remember, we have 500 milligrams in stock, or sorry, 500 milligrams that is being ordered. And in stock, we have that 250 milligram per 5 mil suspension. So dimensional analysis, always start with the unit that we're looking for. So we're looking for the dose volume. So the unit of volume would be milliliters. And we want to keep that unit on top in our first fraction. Well, all we know so far about mils is that in each 5 milliliters, there are 250 milligrams. Now, I want to be left with just milliliters, so I want to cancel out this milligram. How I do that is set up another fraction that has milligrams on top. Well, I've already used my strength, So all I have left is my order, which is 500 milligrams. And that is just by itself, so we can just put that over 1. So now my milligrams will cancel, and I'll be left with mils, which is what I want. So now I can solve. So 5 times 500 is 2,500. 250 times 1 is just 250. When we divide those, we still end up with 10 milliliters for our dose volume. Okay, so I am on page 165. I'm looking at number 3 in the pretest. So here we have a physician orders Tylenol 5 grains every 4 hours as needed for fever and aches for a child who has a high fever. The drug available is acetaminophen suspension, 160 milligrams per 5 mLs. What volume is needed per dose? Round to the nearest whole number. So the order here, they're ordering 5 grains every 4 hours. So we're looking for the dose volume. So all we care about is how much they're getting at one time. So that 5 grains. And in stock, we have a suspension that is 160 milligrams per 5 milliliters. Now, I can clearly see that I have 2 different units here. I have grains, which is apothecary, and I have milligrams and mils, which is metric. So the first thing I need to do is convert these grains into milligrams. That way I can set up either ratio and proportion or dimensional analysis. So what's important here is the drug. So the drug is acetaminophen. So we need to take a look at those tables from chapter 6 that I printed out for you. So remember, when we're going from grains to milligrams, certain drugs have different conversion factors. So acetaminophen here says that 1 grain equals 65 milligrams. So if we know that 1 grain is 65 milligrams, we can set that equal to our 5 grains to figure out how many milligrams that would be. So 65 times 5 gives us 325 milligrams. And that would just be 1x, which we would just divide by 1. So that's still how many milligrams we would have. So 5 grains is the same thing as 325 milligrams. Now that we have the same units, we can set this up. So first, I'll use ratio and proportion. So we have in stock 160 milligrams per 5 ml solute suspension, and we need 325 milligrams. So set that equal here. So milligrams equal milligram. We're solving for the dose volume, and we know that volume, our unit is milliliters. So cross multiply, we have 160x equals 325 times 5, which gives us 1,625. To get x by itself, we divide by 160. And x equals 10.2, roughly, is 10.156. So I just rounded to the nearest tenth, 10.2 milliliters here. Now, if I wanted to do this with dimensional analysis, we could do that as well. Remember, we're looking for the dose volume, so we need to be starting with milliliters and starting with a fraction that has milliliters on top. So all we know is that my solution in every 5 mils, there are 160 milligrams. To get rid of the milligram, I need to multiply by a fraction that keeps milligrams on top on this next fraction. And I've already used my stock, so the only thing that's left is my order, which was 325 milligrams. That is by itself, so we can just put that over 1. Our units, our milligrams will cancel, and we can solve. So once again, 325 times 5 gives us 1,625. 160 times 1 is just 160. And then once again, when we divide those, we get roughly 10.2 milliliters. Now, the problem, it did say round to the nearest whole number. So the nearest whole number, well, 2 is not less than, or not more than 5. So we just round down to 10 milliliters, and that would be our dose volume. Okay, number 5. A physician orders Benadryl 25 milligrams 3 times a day as needed for severe itching. The strength available is diphenhydramine 12.5 milligram per 5 ml. What volume is needed per dose? So once again, we're looking for our dose volume, which means we're looking for milliliters. So our order, remember the dose is how much they're taking at one time, so I just care about the 25 milligram. And my stock, I have a 12.5 milligram per 5 ml solution. So these are in the same units, so we can just use a simple ratio and proportion here. So ratio and proportion, 12.5 milligrams per 5 mils. Set that equal to what I'm looking for, which I need 25 milligrams. X will give me that volume. So 25 times 5 gives us 125 equals 12.5x. To solve for x, I need to divide by 12.5. And I am left with 10 milliliters. Now I'll go through dimensional analysis just so we can make sure that we are getting this process. So dimensional analysis, start with what you want. We want to find mils. Keep that on top of your first fraction. So all I know here is that in every 5 mils, there are 12.5 milligrams. To cancel out my milligrams, I need to have milligrams on top. All that I have left is my order of 25, which is by itself. Milligrams cancel. Once again, 5 times 25 is 125 divided by 12.5 still gives me 10 milliliters. So my volume per dose would be 10 mils. Now it says what volume is needed in household measurements. So remember, milliliters are metric. So they're asking us if we were measuring this in household, what unit could we use? Well, if you are, hopefully you're getting familiar with some of these units here. One that we use most often, probably in oral meds, oral liquid medications, would be the teaspoon or the tablespoon. So we see that 1 teaspoon is 5 mLs, which if you can see that in your head, that's perfectly fine. You know, if 1 teaspoon is 5 mils, then 10 mils would be 2 teaspoons, right? But if you didn't see that, that's perfectly fine. Just use that conversion factor. We know that 1 teaspoon is 5 mils. So if we have 10 mils, how many teaspoons would that be? Well, 5x equals 10. So we could divide by 5, x equals 2 teaspoons. Okay, so reconstitution of powders into oral liquids. We use the reconstitution process a lot with oral suspensions. So reconstitution is the process of dissolving a powdered medication in the appropriate liquid or diluent, also known as a solvent. So here I have an example of a suspension. So suspensions usually come in powder form, like so here, if you can see that. Um, so here we have cefprozil oral suspension. It is a total of 75 milliliters when reconstituted. So after I add water to this, it'll have a total of 75 mils. The strength will be 125 milligrams per every 5 mLs. So anytime you have a suspension that comes from the manufacturer like this, and it needs to be reconstituted, you must read the instructions on the side. So this one's a little fuzzy here, but it says directions for mixing. Total 70 mils of water to be added. Now, when we reconstitute antibiotics or any oral suspension, we usually use distilled water. So you're not just going to use water from the sink. So the water amount to be added is 70 milliliters. So that's what we call our diluent volume or our solvent volume, okay? When we're done mixing this together, it's going to have a total volume or a final volume of 75 mils. But what we're adding is only 70 mils. So what that means, excuse me, when this powder dissolves, it's going to take up space of its own. And we can solve for the powder volume simply by subtracting the diluent volume from the final volume here. So 75 minus 70 would give us 5 mils. So even though this powder is measured in weight, once it dissolves and takes up space, it will take up 5 milliliters of space. So that's what we call our powder volume. So final volume, diluent volume, subtract those to find your powder volume. In this case would be 5 mils. So when we're adding water to a suspension, we don't just add a total of 70 mils right off the bat. Usually this powder is very staticky and it tends to clump together. So make sure you read the directions on the side of the bottle. So it says tap bottle till all powder flows freely. Add approximately half of the total amount of water. Shake vigorously to wet powder. Then add remaining water and again shake vigorously. So that's what we usually do, roughly a half to 2/3 of the water added first, shake really well, add the rest, shake really well again. Not just because we want the drug to be evenly distributed, make sure that it all evenly dissolves. Also on the side of your bottle, you should have important information. So almost all suspensions will say shake well before using. That's because they tend to suspend. The particles are suspended, hence the name there. This one, it says refrigeration preferable but not required. So that's very important. A lot of antibiotics do need to be refrigerated. So you always got to make sure you check that. And then this says discard the suspension after 14 days. Okay, so even though on the side here, which this one is a little outdated, but the expiration date was January of 2020. Okay, so the expiration date that's marked on here is given by the manufacturer. Now, when we reconstitute a suspension, the expiration date is going to drastically decrease. Even though this bottle is expired, let's pretend that this said, January of 2022. Okay, so we have almost a year before that would expire. But when I add water to this, when I reconstitute it, it's only good for 14 days. So that's what we consider the beyond use date. So you would take today's date plus 14 days. That would be when this bottle would expire. So always make sure that you're reading your label very carefully, following all of the reconstituting instructions and the storage information as well. If you're using a graduated cylinder to measure out your distilled water, once again, measure at eye level and measure from the bottom of the meniscus. So I discussed the difference between the final volume, the diluent volume, and the powder volume. So if we take a look at this label here, we can see that the strength of the suspension is 125 milligrams per 5 mLs. The final volume will be 100 mLs when it's reconstituted. And then if we read through here, it says directions for mixing. This one actually says 1/3 of the water. So it's always, roughly just 1/3, 1/2, 2/3. Just depends on the manufacturer. But it says a total of 78 mils. So this is what we would measure out. So that's going to be our diluent volume. Now remember, to find the powder volume, we just subtract the two. So for example, 100 mils, which was our final, minus 78, which was our diluent volume, gives us our powder volume, which would be 22 milliliters here. Okay, so I'm still on the pretest. I'm on page 166 if you want to follow along in the book. I'm going to go over number 10 here. So a bottle of ampicillin is marked 125 milligrams per 5 ml. The 200 ml bottle instructs that 158 ml of water be added for an oral suspension. The physician wants the child to receive ampicillin 250 milligrams 4 times a day. So a lot of information is given to us here. First question says, what volume of water should be added to the powder? Well, it just told us that it says the 200 ml bottle instructs that 158 ml of water be added for the suspension. So the volume to be added would be the 158 milliliters. Now it says, what is the powder volume? So remember, we take our final volume minus our diluent volume to find the powder volume. So final volume here was 200 mils. The diluent volume, or the water we're adding, was 158 mils. And so if we subtract those, we can find the powder volume. So 200 minus 158 gives us 42 mils there. So powder volume, 42 milliliters. Now it says, what is the volume per dose that the child should receive? So we're looking for the volume per dose, or the dose volume. Dose is what's given at one time. So the physician wants a child to receive 250 milligrams each time. So the dose, or the order, is 250 milligram. And we're looking for the dose volume. So we need to look at the strength of our solution. Well, it says that we have in stock, our bottle is 125 milligrams per 5 mLs. And we're looking for the dose volume. So remember, dose volume, set your order equal to your strength. So the order is 250 milligrams. We're looking for that volume. And we know that we have 125 milligrams per 5 mLs in stock. So 250 times 5 gives us 1,250. And we're setting that equal to 125x. So divide by 125. X gives us 10 milliliters. So that is our dose volume. If I pour out 10 milliliters of the solution, it's going to give me that 250 milligrams. So the dose volume would be 10 mils. And then it says, what is this dose in household measurements? Which is very similar exactly to what we just did in the previous problem. So remember, if 1 teaspoon is 5 mils and we want 10 mils, well, if we solve for this, X is still 2 teaspoons. So in household measurements, we would give them 2 teaspoons. Now, on some of your problems, they're going to ask you to draw on cylinders or syringes or droppers. I think there's only a few in chapter 9. Like on number 12 on practice A, it wants you to show that on the dropper. You can go ahead and just skip those. You do not have to draw out those syringes or cylinders in your actual assignment. Okay, so I want to go through one last problem here. It's a pretty long one, but it won't take very long. So I'm on page 184. I'm on number 10 on the post test. So it says, first question says, what is the total volume after reconstitution? Okay, so we're looking for volume. Remember, volume is going to be milliliters. And it says after reconstitution. Well, if I look at my label, here it says 75 mils when mixed. So after it's mixed or reconstituted, 75 mils will be my final volume. What is used as the diluent for reconstitution? So it says what is being used as the diluent. So we're going to need to read. It says add 45 mils of water in 2 portions to the dry mixture. So looks like it just says water. Yeah, it doesn't specify here, but we always want to use distilled water. So distilled water would be what we use. What volume of diluent is added? Well, the diluent volume says add 45 mils of water. So 45 mils. Show the volume on the graduate. Once again, if you have problems like this, you don't have to do that. But just for this purpose here, we're reading this graduate. Well, here's 40, here's 50, so 45 would be right there in the middle, right at that hash mark. What is the powder volume? Well, remember, powder volume is always final volume minus diluent volume. So 75 minus 45 gives us 30 mils as our powder volume. Now it says, what is the medication concentration after reconstitution? Well, concentration is the same thing as strength. And remember, the strength of any liquid is always weight per volume. So here, right on the front, it says we have 200 milligrams per 5 mLs. So 200 milligram per every 5 mLs. Now, what volume is needed for a 400 milligram dose in milliliters? So we're looking for milliliters, and the dose is 400 milligrams. So we're looking for a dose volume. So dose volume, always set the order equal to your strength or your concentration. So 400 milligrams is in, well, we don't know how many mils will give us that, but we do know that 200 milligrams is in every 5 mLs. Well, if you can see, visually, well, 200 is half of 400. So we're going to need twice this amount, right? So we're going to need 5 times 2, which would give us 10. Okay, so if you're starting to pick up on these things, that's great. If not, set the problem up and you can still solve it just the same here. So we have 200x equals 400 times 5. So 400 times 5 would be 2,000. And then we would divide by 200, divide by 200. X would give us 10 milliliters. Okay, so now it says what volume is needed for a 400 milligram dose in household measurements? Well, we just said that 400 milligrams would be 10 mils, and just in 2 problems that I've already done, we've already established that 1 teaspoon is 5 mils, so 2 teaspoons would have to be 10 milliliters. Now it says, what are the storage requirements before reconstitution? So we're going to need to read a little bit on the label here. So let's see. Store at room temperature. So that's going to be, the storage instructions. It doesn't specify that this has to be refrigerated after reconstitution either. Just making sure that I didn't miss that. Nope, so it just says store at room temperature. So both of these questions, before and after, it says store at room temperature, and same answer for that one there. Now it says, how long is the medication potent after reconstitution? So how long is it good for after we reconstitute it? Well, if we look back up here and read, it says may be kept for 14 days without significant loss of potency. So here we see 14 days would be our answer there.